Welcome back, curious minds, to another Neural Intel deep dive. For decades, honestly, the dream of having AI truly reason mathematically, to prove theorems with the rigor, the creativity of a human genius, it seemed almost impossibly distant.
It really did.
But today, we're unpacking a groundbreaking paper that suggests that dream is now closer to reality than ever before. We're venturing into the fascinating world of automated theorem proving, where artificial intelligence is not just crunching numbers, but genuinely pushing the boundaries of mathematical insight.
Indeed, it's a domain that bridges the cutting edge of AI with the foundational principles of formal logic. And we're talking about systems now capable of verifying complex mathematical proofs with a precision, a scale that human experts often cannot match.
So our mission for this deep dive, as always, is to really dissect the technical innovations behind these advanced automated reasoning systems. We want to understand their methodologies, explore the implications, particularly in fields like formal verification.
Exactly. We'll focus purely on the technical advancements and the how behind their impressive performance. As always, you can find links to the papers and resources on our webpage, linked in the bio if you want to follow along or dive even deeper after the show.
Absolutely. And the paper we've got our hands on today is truly remarkable. It's titled Seed Prover, Deep and Broad Reasoning for Automated Theorem Proving, from ByteDance Seed AI4 Math. This paper introduces two new systems, Seed Prover and Seed Geometry, which have achieved results that are, well, frankly, astonishing. They've tackled, and in many cases conquered, problems from the International Mathematical Olympiad, the IMO.
Yeah, problems designed to challenge the absolute brightest young mathematical minds on the planet. It's serious stuff.
So as we embark on this deep dive, what's the first crucial concept we need to grasp to understand this evolving landscape? Where do we start? Hashtag one, the evolving landscape of automated theorem proving.
Okay, so to really understand the leap seed prover represents, we first need to appreciate the foundational distinction it builds upon. The paper starts by reminding us that large language models, LLMs, have shown some pretty impressive mathematical reasoning abilities, right?
Right. We've seen them solve word problems, do some basic algebra.
Exactly. But there's a key challenge, and this is absolutely fundamental to unlocking their full potential. Natural language proofs, the kind humans write, are incredibly tough to verify automatically.
Okay, hang on. That immediately raises a question for me. If an LLM can generate a convincing, human-readable chain of thought in natural language, why is it so fundamentally difficult to then verify that reasoning? What's the missing piece that formal languages like Linnean provide? Why is that so transformative for the AI's ability to learn?
That's a critical distinction. Natural language, well, it's incredibly flexible. It's intuitive for us humans, right? But it inherently lacks the unambiguous structured framework you absolutely need for automated verification. When a human writes a proof in, say, English, there are often implicit steps, maybe some informal reasoning jumps, a reliance on shared understanding or intuition. Things a machine just can't parse without significant ambiguity.
So it's too fuzzy for a computer.
Pretty much. It makes it extremely difficult, maybe impossible, for an automated system to consistently and correctly check each step for validity. Think about trying to teach a machine to drive by just saying, go a bit faster or turn leftish. It needs precise signals.
Right. Makes sense.
Lean, on the other hand, provides that rigorous rule-based framework. Every single inference, every definition, every axiom is explicit and, crucially, machine parsable.
Oh, okay.
This allows systems to receive clear binary feedback, correct or incorrect on each step, or even on entire blocks of a proof. This verifiable answer is what transforms abstract mathematical statements into concrete machine-verifiable code.
And that's the bedrock for reinforcement learning.
Exactly. That's the bedrock for effective reinforcement learning. Without that clear signal, an AI simply can't know if its actions are leading it closer to a correct proof. Learning becomes incredibly inefficient, maybe even impossible for complex proofs.
Got it.
And this is why works like AlphaProof are so noteworthy. They demonstrate that LLMs, when you couple them with formal languages like Lane, they're capable of proving very challenging problems, even tough IMO problems, that LLMs relying only on natural language just can't crack.
So it's a real shift towards formal methods for these high-stakes tasks.
It truly highlights a significant shift in the landscape, yes. Moving towards formal methods for verifiability and, importantly, for robust AI learning.
I can absolutely see how that clear machine-verifiable signal is the bedrock for effective learning. It's almost like giving the AI a precise compass in this vast, complex mathematical jungle.
That's a great analogy.
Now, building on that, once these models have that compass, how do they actually navigate the proof-finding process? The paper draws this fascinating distinction between step-level provers and whole-proof generation provers. Could you clarify the technical nuances between these two philosophies? And critically, why did seed prover choose the whole-proof path? It sounds like that might bring its own computational challenges.
Yeah, it does. The distinction lies primarily in their granularity, how fine-grained their proof generation is, and how they interact with the lean environment. So step-level provers operate incrementally. They generate lean code line by line, or maybe tactic by
Yeah,
tactic.
tiny steps.
Tiny steps. This allows for very granular interaction with lean. The model can get feedback after almost every small step.
Which sounds good, right? Immediate error correction.
He's beneficial, yeah.
But it comes with significant drawbacks. It can be incredibly slow because of that constant back and forth with the lean compiler. Each small step needs a new LLM inference, a new compiler call. That adds up to substantial latency.
Lots of overhead. A lot of overhead. Plus, it often requires extensive scaffolding. Essentially a complex support structure, just to guide the generation of a complete proof. And this fine-grained interaction can sometimes hinder higher-level, more abstract reasoning. It's hard for the AI to see the forest for the trees, so to speak.
Right.
In contrast, whole-proof models are designed to generate an entire lean proof at once, a single contiguous block of code.
Like writing the whole essay before proofreading.
Kind of, yeah. Traditionally, these models lack direct interaction with the lean compiler during the generation itself. They generate the whole thing, then check it. If it failed, well, start over.
That sounds risky.
It can be. But Seed Prover innovates significantly here. It adopts this whole proof approach, but adds a really powerful iterative refinement mechanism after the initial generation.
Ah, okay. So it generates the whole thing, then debugs it.
Exactly. It combines the coherence and potentially the speed of generating a complete thought with the ability to learn from compiler feedback on that complete thought. It's a crucial leap forward.
That innovation sounds like it's directly addressing a core limitation of those traditional whole-proof models. But thinking about these whole-proof models, especially one generating, say, a full found line proof, which the paper mentions, what are the computational trade-offs versus step-by-step? What kind of memory or processing power are we talking about for something that long?
That's an excellent question, and it really points to a critical engineering consideration behind Seed Prover's design. For a whole proof model generating hundreds or even over 1,000 lines of lean code, the computational overhead is definitely substantial. It just shifts, from frequent smaller interactions to fewer but much larger generation and verification tasks.
Okay.
The primary trade-off is between latency per interaction and total computational throughput. Step-level provers, they have high latency because of all those compiler calls and context switches. For a 1,000-line proof, potentially 1,000 separate LLM inferences, 1,000 compiler checks, that's a bottleneck.
Yeah, sounds slow, like laying one graph waiting for approval, laying the next.
Precisely. Slow and methodical. Whole proof generation, especially for 1,000 lines, needs a very large context window for the LLM to maintain coherence, right? To keep track of the logical flow across the entire proof.
So big memory demands.
Big memory demands, particularly VRAM on the GPUs to hold the model weights in those long input-output sequences. The cost for a single pass through a transformer generally scales quadratically with sequence length. So generating 1,000 tokens in one go is significantly more expensive than, say, generating 10 tokens 100 times computationally.
But maybe faster overall.
Potentially faster overall because you avoid the overhead of thousands of separate interactions. And Seed Prover's iterative refinement happens on the generated proof, which is smarter debugging. But yes, for a 1,000-line proof attempt, you are definitely talking about significant high-end GPU resources and substantial inference time per attempt, even with optimizations.
Okay, that makes sense. And it really sets the stage for understanding Seed Prover's core features, like that iterative refinement and the scaling strategies you mentioned. So Seed Prover is a whole proof model, but it's clearly got some really clever features to handle those challenges and boost its reasoning. The first one that jumps out is lemma-style proving. This sounds incredibly intuitive, almost exactly how human mathematicians work, right? Breaking down big proofs into smaller steps.
That's exactly right. It absolutely mimics human problem solving, but it's implemented in a very precise, technically rigorous way.
Yeah.
Instead of just trying to prove the main theorem directly, which can be, frankly, overwhelming.
Yeah, like trying to climb Everest in one go.
Good analogy. Seed Prover is explicitly designed to first generate useful intermediate lemmas. Think of these as highly specialized building blocks or stepping stones. And this approach offers several profound technical merits for the AI.
Of course, like what?
Firstly, modularity. Each lemma can be compiled and verified independently by the lean compiler. This is key. If a lemma fails, the system knows exactly where the error is, instead of debugging a huge monolithic proof.
Much easier to pinpoint problems.
Definitely. And successfully verified lemmas. They get stored in a dedicated lemma pool. They can be freely combined, reused, referenced in later proof attempts for other lemmas or the main theorem. It makes the whole process much more flexible and robust, like a software engineer reusing well-tested code modules.
That makes a lot of sense. What else?
Secondly, it provides direct and granular progress tracking. By clearly identifying which lemmas are proved and which aren't, the system gets an unambiguous signal of its progress towards the main goal.
Like checkpoints in a video game.
Sort of. It acts as a kind of intrinsic reward signal, helping guide the AI, letting it focus its computational effort where it's most needed. Thirdly, proved lemmas can provide crucial inspiration. They guide the model when tackling unproved ones or the main problem. It's like the AI having a library of solved examples during the reasoning process itself. These solved lemmas offer patterns, proof techniques.
So it learns from its own successes mid-problem.
In a way, yes. And finally, that lemma pool I mentioned. It's quite sophisticated. It stores comprehensive data for each difficult problem. Lemma statements, names, proofs, difficulty scores, even dependency relations. And it's actively used. It can retrieve relevant lemmas or sample difficult ones for the model to focus on. It's like a built-in knowledge management system.
Wow.
If you look at Figure 2 in the paper, it shows this really well, the contrast between a simple whole proof and the lemma-style approach in Lean 4. You see the lemma and theorem keywords clearly, and how tactics like iterative can combine these subproofs. It makes the AI's process much more structured and, importantly, auditable for us humans.
That's incredibly elegant, mimicking human decomposition but gaining real technical advantages. Now, beyond the lemma-style approach, you mentioned it also iteratively refines its proofs based on lean compiler feedback and self-summarization. That sounds like an extraordinarily powerful feedback loop, much better than just one shot.
Oh, absolutely. This iterative refinement is, without doubt, a cornerstone of seed prover's success. It means the model doesn't just try once and give up. It engages in a continuous learning and debugging process.
How does that work exactly?
So if an initial proof attempt, or maybe a lemma, fails the lean compiler check, it doesn't just get a failed signal. Critically, it receives specific feedback from lean about what went wrong.
Like a syntax error or a logic gap.
Exactly. Syntax errors, type mismatches, maybe unmet preconditions for a tactic, or a fundamental logical inconsistency. That detailed feedback is invaluable.
Okay.
The model then combines this precise compiler feedback with a self-summarization of its own previous attempt. It's essentially reflecting, okay, what did I try? Why did it fail? How does this specific error message relate?
So it reflects on its own reasoning.
Right, and it uses this rich context to refine and try again. It might completely alter its reasoning trajectory based on that new information. This is where having that long chain of thought capability combined with concrete verifiable feedback really pays off. It's like a human mathematician debugging their own proof, learning from specific errors.
Not just general failure.
Exactly. And why this matters so much technically is it tackles the sparse reward problem in reinforcement learning for complex tasks like theorem proving.
Ah, right, where you only know if you succeeded or failed at the very end.
Precisely. Imagine teaching a robot to assemble a complex engine, and the only feedback is fail or success after hours of work. How does it know which tiny action caused the failure?
Impossible.
The lean compiler here acts like giving that robot a detailed diagnostic readout at every stage, even on the whole proof attempt. This structured granular feedback loop lets seed prover continuously improve. It transforms abstract failures into actionable learning opportunities. That's genuinely revolutionary for AI in these deep reasoning domains.
That capability is profound, turning errors into learning fuel. And then there are the test time scaling strategies, light, medium, and heavy. This sounds incredibly sophisticated, like the AI dynamically adjusts its thinking effort. Can you walk us through how Seed Prover allocates its thinking budget across these tiers? What kind of problems is each designed for? And what's the computational overhead? That must scale up significantly, right?
Absolutely. These strategies are really a masterclass in dynamic resource allocation for automated reasoning. They show Seed Prover isn't a one-size-fits-all engine, it's a flexible problem solver. It adapts its reasoning depth and breadth based on the problem's difficulty and, crucially, the available compute resources. And yes, the computational overhead scales significantly with each tier. It's a very deliberate trade-off.
Okay, let's break them down. Start with light.
Right, the light inference setting. mechanism. Here, Seed Prover focuses on refining each proof attempt iteratively, usually doing 8 to 16 refinement steps. It uses that lean compiler feedback and self-summarization for each step. The paper notes this is quite efficient computationally, roughly equivalent to generating a whole proof at pass at 64 to pass at 256.
What does pass at k mean again?
Right, pass at k usually means running the model k times independently and picking the best result. So the light settings iterative refinement achieves similar exploration breadth to running the model, say, 64 to 256 times, but it does it smarter, more targeted, within one iterative process. Much more efficient.
Gotcha. So better than just brute force sampling.
Exactly. The technical impact is a significant improvement over single-pass inference, which often fails on harder problems. It's about deepening the reasoning on one promising path. Observe behaviors. We see it fix lean syntax errors, type errors, fundamental stuff. But more profoundly, it refines initial proof sketches, sometimes completely altering the reasoning trajectory. That shows real learning and correction. Example, a big win was proving IMO 2022 Problem 2. That has a MOHS score Math Olympiad hardness scale of 151. Anything over 100 is super tough. 151 is extreme territory.
Wow.
Seed Prover solved it in just 1-2 hours using the light setting. Without refinement, the paper estimates it would need a massive pass at 8192 budget. Huge efficiency gain. Computational overhead, light. It's more than a single pass, sure, but it's contained. Multiple LLM runs on refined prompts, repeated lean checks. Manageable, minutes to a few hours on a good GPU.
Okay, that's light. What about medium?
The medium inference setting mechanism. This introduces hierarchy. There's an outer refinement loop for the main problem, like the light setting. But simultaneously, there's an inner refinement loop that targets difficult intermediate lemmas generated by the outer loop.
So it drills down on tricky subproblems.
Exactly. These inner refinements use a light setting, maybe an 8x8 budget, 8 attempts, 8 refinements each. If an inner loop successfully proves a lemma, that new fact is immediately fed back into the prompt for the outer refinement.
So it learns and uses new lemmas on the fly.
Yes. The technical impact is handling longer, structurally complex proofs, maybe over 1,000 lines. It can tackle subproblems while keeping the main goal in sight. Examples. Solve tough ones like IMO 2003 P6, MOHS 35, IMO 2020 P5, MOHS 20, IMO 2024 P1, MOHS 5, and IMO 2025 P5, MOHS 15 this way. Problems needing multiple steps and subproofs. Computational overhead, medium. Significantly more intensive than light. You're running light-level refinements potentially recursively on multiple subproblems. Needs more compute, maybe hours or even a day for complex problems. More state management, too.
Right, makes sense.
And the final tier, heavy. Sounds like the big guns.
That's the heavy inference setting, the most complex and computationally demanding mechanism. It combines deep reasoning with really broad exploration. It starts by generating a huge conjecture pool, maybe 5,000 potential conjectures, using a dedicated proposer module.
5,000 hypotheses. Wow.
Yeah. Then it tries to prove or disprove each conjecture using the light setting. Successfully proved ones go into the central lemma pool. And the proposer module isn't static. It can generate more conjectures based on the lemmas already proved. It's a dynamic loop.
So it keeps exploring based on what it finds. Exactly. This can run for days of thinking, accumulating thousands of non-trivial math facts. These lemmas are then scored. Low proof rate suggests high value, semantic relevance judged by an LLM, proof length. Hundreds of the top-ranked lemmas are then fed into the medium setting to help solve the main problem. And crucially, Seed Prover is trained via RL to actually select and use these external lemmas effectively. Technical impact. Addresses problems needing extensive groundwork or novel auxiliary steps. It provides the breadth you can't get from deep reasoning alone. Like a massive team exploring every angle. Examples. Problems like IMO 2017 P2, MOHS 40, IMO 2025 P3, MOHS 25, and IMO 2025 P4, MOHS 15 needed this heavy setting. Often problems where a key intermediate result is hidden. Computational overhead, heavy, very intensive, generating thousands of conjectures, trying to prove each, scoring, feeding into medium. You're talking multiple high-end GPUs running for days, potentially weeks. Significant cost, robust distributed setup needed. It's a massive investment in deep mathematical exploration.
That conjecture proposing in the heavy setting is particularly fascinating. It really sounds like the AI is doing more than just proving. It's exploring, hypothesizing, almost like human mathematical discovery. What's the technical distinction from previous chain-of-thought methods that just aim straight for the solution?
That's a crucial innovation, and you've nailed why it's so powerful. Unlike many prior chain-of-thought methods, aiming for a linear sequence of steps towards the final proof.
Like, to prove A, I need B. To prove B, I need C.
Exactly. Seed Prover's proposer module emphasizes broad exploration of the problem space. Its objective is different. It's tasked with enumerating potentially useful properties without necessarily committing to a deep proof path for each one right away.
Can you give an example?
Sure. Faced with a functional equation problem, instead of directly trying to prove, say, fx, x is x, the proposer might hypothesize, is the function injective, surjective, bijective, monotonic, periodic? These are general properties. They might be true, might not be. But if proved, they could be incredibly valuable intermediate lemmas.
So it's brainstorming possibilities first.
Yes. It's not trying to solve the problem at this stage. It's performing a wide-ranging parallel generation of maybe 10 to 50 candidate conjectures based on the problem context. This hugely increases the diversity of approaches and the chance of uncovering a valuable property, a key lemma.
How does that differ from, say, draft, sketch, prove?
That approach typically presumes you can sketch a full solution up front and then refine it. Seed Prover's method doesn't make that presumption. It performs this broad exploratory search first, generating hypotheses and then trying to validate them. It allows the system to discover fundamental characteristics that might be non-obvious or require a completely different line of thinking than a direct proof attempt would find.
It's like casting a wide net for insight.
Exactly. Much like a human mathematician might spend hours just exploring different facets of a problem before hitting the right approach. It's a strategic shift from deep, narrow search to broad, parallel exploration.
That's a truly sophisticated design, automating that crucial brainstorming phase. Given how complex seed prover is iterative refinement, a lemma's 3 inference tiers, how do they actually train this beast? What does multi-stage, multitask reinforcement learning really mean here?
The training is indeed quite intricate, showing the sophistication of modern RL applied to formal reasoning. It uses a multi-stage, multitask RL approach based on VAPO, which is a particularly effective policy optimization technique. Think of it as an iterative process where the AI learns the best sequence of actions to get a proof, refining its strategy based on whether lean verifies its attempts.
Okay, multi-stage and multitask.
Multi-stage refers to a curriculum learning approach. They progressively train the model on harder and more diverse problems over time. Multitask means it learns to do different things simultaneously, like proposing lemmas and generating full proofs.
How does the reward work? Is it complex?
It's surprisingly simple at its core. The reward is basically 1 if the statement is proven by lean, 0 otherwise. That's the fundamental feedback. But cleverly, they also add a formatting penalty if the model doesn't generate lemmas first.
Nudging it towards that lemma-style.
Exactly. It shapes the model's behavior. And critically, as training progresses, they gradually increase problem difficulty, quality, and the allowed output length. Standard curriculum learning, building foundational skills first.
What about the training data itself?
Their data strategy is key, a mix of open source and in-house formalized problems. For problems too hard for the model to solve initially in training, they actually use their proposer module, the same one from heavy inference, to create easier variants.
Like generating lemmas for it to prove.
Precisely, giving it solvable challenges. Conversely, problems that become too easy, proof rate 14, get excluded from RL training. Keeps the focus on tasks where it can actually learn and improve.
Smart filter.
And maybe one of the biggest technical advancements in their training, compared to prior work, which often just use formal statements as prompts, is their highly diverse prompting strategy. The prompts for RL training randomly mix in a rich array of info.
Like what kind of info?
Natural language hints, natural language proofs, similar lemmas seen before, successfully proved lemmas, failed lemma attempts, summaries of previous tries, and critically direct lean compiler feedback.
Wow, that's a lot of context.
It's a technical marvel. This rich prompting enables the model to effectively understand and leverage all the feedback and context it gets during that complex multi-stage inference pipeline. Without it, the iterative refinement and multi-tiered search wouldn't be nearly as effective. It teaches the model to interpret and react to a very complex environment. That's vital for its adaptability and performance.
That level of detail in the training really showcases the engineering. Now, one big challenge the paper flags is geometry. Lean is powerful, but geometric reasoning often needs visual intuition, adding lines, circles, auxiliary constructions. That's where seed geometry comes in, right? How does it tackle this gap? And what makes it neurosymbolic? We hear that term more and more.
That's a crucial point. Geometry problems often require a very different kind of reasoning. The core challenge for automated provers is exactly that, the need for auxiliary constructions, adding lines, points, circles that aren't explicitly given but are essential for the proof.
Stuff humans just see on the diagram sometimes.
Exactly. Lean, as a general formal language, doesn't inherently know how to make those creative geometric leaps. It's built for logical deduction from explicit statements, not for drawing new lines to reveal hidden properties.
So how does seed geometry bridge that?
It acts as a dedicated geometry reasoning engine, and it's neurosymbolic because it ingeniously combines two distinct AI paradigms. The neuro part is a neural model, a large language model trained specifically to propose these missing auxiliary constructions.
So the LLM does the creative bit, suggests where to draw the line.
Precisely. That's where the intuition, pattern recognition, maybe even a simulated visual understanding comes in. It generates hypotheses for new elements. The symbolic part is a classical rule-based reasoning engine. It takes these proposed constructions and performs step-by-step forward-chaining derivations to logically complete the proof.
Okay, so neural proposes, symbolic proves.
In essence, yes. The symbolic engine methodically checks known facts, applies geometric rules until no new facts can be derived, reaching closure, then traces dependencies backward to confirm the proof. This separation lets the neural part handle the creative exploration, while the symbolic part ensures rigorous, precise verification.
How do you even train the neural part to be good at that creative step?
That's where data comes in. Seed Geometry established a massive repository, 230 million unique geometry problems that require auxiliary constructions, derived from over 20 years of math Olympiad statistics.
230 million, that's huge.
It's enormous.
Yeah.
And absolutely key to training the neural model effectively. It lets the model learn the geometric intuition needed for creative problem solving by seeing countless examples.
That's a fantastic explanation of neurosymbolic. The paper mentions seed geometry builds on something called tongue geometry, but with a major redesign. When I see major redesign, I expect big technical breakthroughs, not just tweaks. What are the upgrades that make it a substantial upgrade?
You're right to pick up on that. The paper is clear. This isn't just a minor update. It's an extensive, critical redesign that fundamentally boosts performance over tongue geometry. Several key technical upgrades make it a massive leap.
Okay, what's the first one?
First, an extended domain-specific language, DSL. Traditional ruler and compass steps can be incredibly verbose in formal language. Imagine describing every tiny arc, every intersection.
Yeah, it sounds tedious and long.
Exactly. Huge burden on the neural model processing it and the symbolic engine deriving from it. So, seed geometry groups complex action sequences into concise, composite actions. Think higher-level geometric operations like isogonal conjugate or similitude centers.
Stuff competitive geometers uses shortcuts.
Precisely. While they break down into primitive steps, formalizing them as single actions makes the language much more concise, reduces sequence length for the neural model, streamlines symbolic derivation. It lets the AI think at a higher abstraction level. It's an elegant way to manage complexity.
Smart. What's next?
Second, an extremely fast reasoning engine. This is the monumental leap. The entire backend symbolic engine was completely rewritten from Python into C++.
Ah, C++ for speed.
Massive speed.
Yeah.
We're talking a roughly 100-fold speed increase compared to the Python predecessor in tongue geometry.
100 times faster. That's incredible.
It's game-changing. C++ gives better memory control, benefits from compiler optimizations. The result is much faster, deeper searches in the reasoning engine. Absolutely vital for forward-chaining derivation, where the search space explodes.
Yeah.
It implies a huge engineering effort went into optimizing that core engine.
Okay, faster engine, better language. What else?
Third, an exceptional large language model. Seed Geometry uses a high-performing seed model from that ByteDance family, extensively pre-trained on coding and math, gives it broad, relevant skills. Interestingly, they found a single seed model acting just as the policy-proposing auxiliaries was enough for top performance.
Not the usual actor-critic setup.
Right. It contradicts common setups like in tongue geometry, where you have a separate value model predicting path quality or steps remaining. Simplifying to a single policy model streamlines training and solving. Also, the model is trained just on problem context and auxiliaries without a specific target fact goal in the prompt, which also simplifies training.
Interesting simplification. And the last upgrade.
Finally, extensive search capabilities. When given a problem, it first canonicalizes it. If not immediately solved, it starts a sophisticated beam search. The policy model generates multiple proposals per beam, exploring paths in parallel. And thanks to that super-fast C++ engine, it evaluates each proposal quickly.
How does it scale?
It supports distributed setup across multiple GPUs. Each GPU process has CPU thread pools that asynchronously run the reasoning step during the language model inference. This overlaps computation costs the symbolic engine is working while the LLM is making about the next step. Huge speed up for the overall search, making it feasible for complex problems needing vast exploration of auxiliaries. Hashtag tag tag tar4, unpacking the performance and achievements.
This is where it all comes together. We've heard about the smart design, the powerful engine, but what kind of performance gains are we actually seeing? The paper mentions benchmarks like IMO 2025, Mini F2F, Putnam Bench. These are tough tests. How did SeedProver and SeedGeometry actually do?
The results are genuinely impressive, really marking a significant leap. These systems are moving beyond research curiosities into being formidable problem solvers, tackling human competitive math.
Let's start with the big one, IMO 2025.
Right, IMO 2025.
A major highlight. SeedProver and SeedGeometry combined fully proved an astounding 5 out of 6 problems from the contest.
5 out of 6, that's huge for IMO.
It's monumental, considering IMO difficulty requiring novel insights. It's remarkable. Breaking it down, SeedGeometry solved problem 2 almost instantly 2 seconds after getting the formalization. Just blitzed it. Breaking it down, SeedProver solved problem 5 using its medium setting, showing its strength on complex, multi-lemma problems, breaking it down. Problems 1, 3, and 4 needed the heavy inference setting. Problem 1 was actually solved post-deadline, but still it shows the need for that deep, broad search for the very hardest problems.
Really underscores the value of those different inference tiers. One size doesn't fit all. Absolutely. Now, looking at past IMO problems, SeedProver hit an overall success rate of 78.1%, solving 121 out of 155 formalized problems. By difficulty, it's remarkably consistent. 4 to 755 easy, P1, P4, 4 to 756 medium, PTP5, and a really impressive 2,744 hard problems, P2P6. Robust across the board.
Yeah.
By subject, strong in algebra, 7285, and number theory, 4255. Combinatorics, still tougher, only 714 solved.
Yeah, you mentioned combinatorics seems harder for these systems. Why do you think that is? The paper doesn't really dig into why, does it?
No, it notes the gap but doesn't theorize deeply. From our perspective, combinatorics often needs that creative leap, finding a non-obvious projection, a clever counting argument, a novel way to frame things. It's less about systematic rule application, more about finding the trick.
The aha moment.
Exactly. Those moments, or finding very specific combinatorial techniques, seem harder to formalize rigorously, and for an LLM to discover or generalize consistently. The AI excels at deduction within a system, but that initial creative spark, or handling the sometimes tricky formalization of counting arguments, might still be where human intuition has an edge. It's definitely an area to watch.
Fascinating insight. Okay, what about Mini F2F?
On Mini4F, a standard formal math benchmark, SeedProver achieved near saturation. 99.6% proved on both valid and test sets, mostly with the medium setting, just needing heavy for the last few stubborn ones. And here's a key insight I found really interesting. Some problems, like a few from AMC 12 contests, are relatively straightforward in natural language, but pose significant challenges when formalized in lean.
Why?
Usually obstacles in applying specific formulas like Vietas or rigorously counting roots formally. It highlights how AI difficulty doesn't always match human intuition. The strictness of formalization itself can be the hurdle, not just the core concept.
What seems obvious to us can be tricky to code precisely.
Exactly. Now, for Putnam Bench undergraduate level math, SeedProver solved 331 out of 657 problems. Over 50% using just light and medium settings. That's a huge jump from the previous best of 86,657. Shows real strength beyond Olympiads.
Significant improvement there, Combi
Bench. Still a challenge, as we discussed, but it proved 3,100 problems. Way better than the previous 10%, so clear progress, but still room to grow compared to algebra or number theory.
And finally, Mini CTX V2, real-world stuff.
Right, Mini CTX V2. Showed strong potential, solved 81.8% of these contest-rich problems, axiomatic systems, physics analysis, research-level number theory, using only the light setting. This is crucial. It shows generalization beyond contest math, suggesting real utility as a potential research assistant.
That's very promising. And for SeedGeometry specifically, how did it stack up against AlphaGeometry 2, the previous state-of-the-art?
SeedGeometry really established a new SOTA, decisively surpassing AlphaGeometry 2. On the IMO AG50 benchmark, IMO Geometry 2020-2024, SeedGeometry solved 43 problems. AlphaGeometry 2 solved 42. But note, the one problem AlphaGeometry 2 got that SeedGeometry didn't was computation-based. Suggests AlphaGeometry's strength might be more in algebraic geometry methods, while SeedGeometry excels at proof-based problems needing those creative auxiliary constructions. Different strengths.
Okay, interesting nuance.
On the harder IMO shortlist geometry problems, 2020-2022, SeedGeometry solved 22 out of 39, surpassing AlphaGeometry 2's 19. Consistent outperformance on tougher, more diverse problems confirms its capability.
And the speed you mentioned earlier.
Astonishing. Solving IMO 2025 problem 2 in just 2 seconds after getting the formalization. That speed is critical for contests, sure, but it also speaks volumes about the efficiency gains from that C++ backend and optimized search. Unprecedented speed for this level of problem.
Before we wrap up, there's this technical detail you mentioned, buried in the appendix. Looking. It sounds like crucial infrastructure, the plumbing that makes all this high-level stuff work. What exactly is it, and why is it so important for systems like SeedProver?
You're absolutely right to highlight Looking. It's genuinely an unsung hero here, the technical glue making this whole advanced system feasible. Looking is essentially a robust Python interface for Lean, specifically designed to simplify and dramatically accelerate interaction with the Lean theorem prover.
Better than previous interfaces like LeanDojo.
Significantly. It addresses major challenges. LeanDojo, for instance, limited flexibility, only supported older Lean 4 versions, and often required creating a full Lean project for every single interaction, totally impractical for large-scale model development and inference like this.
Okay, so what are Looking's advantages?
Several key technical wins. Its stateless design is fundamental. A Lean state can be processed simultaneously by different Looking instances. Effortless scaling, easy sharing across compute units. Vital for the distributed setups and heavy inference and C geometry search, massive parallel operations become possible. It's version-free. The command line interface lets users manage and switch between different Lean versions easily. Adaptability is crucial as Lean evolves. Keeps the AI systems current. It offers robust memory control. Users can track Lean's memory use, set thresholds to terminate processes if they exceed limits. Hugely important for resource management in large runs, preventing crashes with complex states. Crucially, multi-concurrency support. It can run as a service, handling thousands of concurrent requests via async architecture and resource isolation. This is the enabler for those distributed setups, allowing overlapping computation. Symbolic reasoning happens while the LLM generates the next proposals. Massive speed up. It ensures rigorous proof verification and simplification. Easy way to verify final proofs with native Lean. Plus, it can remove useless tactics hypotheses, simplifying proofs, making them cleaner for humans and for AI training. And finally, statement negation. It can generate the negated form of a statement, useful for proof by contradiction or disproving conjectures, another tool in the AI's arsenal.
So Looking isn't just a convenience. It's really the technical foundation enabling these complex AI provers to interact with Lean effectively and efficiently at the massive scale needed for this kind of research. What does this tell us about the importance of tooling and infrastructure in AI research generally?
It fundamentally underscores that breakthroughs aren't just about the AI models, however big or smart they get. The underlying infrastructure, the tooling that lets these models function at scale with precision. It's equally, maybe even more, critical for real-world deployment and rapid research iteration.
The plumbing matters.
The plumbing absolutely matters. An efficient, flexible, robust interface like Looking isn't an accessory, it's an enabler. Without it, the iterative refinement, extensive search, massive parallel processing that define SeedProver's success, they'd be computationally infeasible or prohibitively slow. It's a testament to full-stack engineering excellence from the low-level compiler interaction up to the high-level algorithms. As AI models get more powerful, the tools managing their interaction with the world must evolve just as fast, often needing equally impressive engineering feats. #tagged I'll take it Taro.
This deep dive into SeedProver and C geometry has really been an exploration of the absolute cutting edge in automated mathematical reasoning. We've seen how formal verification, iteration, sophisticated search, and that crucial underlying infrastructure like Looking are enabling AI to tackle some incredibly hard math problems, even surpassing human performance in some areas. It's a truly compelling look at the technical prowess involved.
These systems really demonstrate the profound effectiveness of integrating large language models with rigorous formal languages like Lean. The ability to get rapid, reliable proof verification, often far more cost-effectively and consistently than human experts can manage. It just opens up vast possibilities. For future math discovery, for verifying complex software or hardware, the technical advancements here are pushing the envelope.
It really makes you wonder, doesn't it? If these systems can now fully prove 5 out of 6 IMO problems, conquer tough geometry with blinding speed. What does this mean for the future of mathematical research itself? Are we heading towards a future where human mathematicians mainly guide AIs rather than doing all the step-by-step derivation themselves?
That's the big fascinating question, isn't it? About the evolving role of intelligence in discovery. If these systems are already so adept at solving established hard problems, and particularly given their technical capabilities in conjecture generation, large-scale lemma accumulation where they can explore space exhaustively in ways humans just can't. How might those capabilities eventually contribute to tackling entirely open conjectures in mathematics? Problems that have stumped humanity for centuries. We're not just talking about solving known problems faster, but potentially generating genuinely novel insights, new mathematical facts.
A true collaboration.
It hints at a future where human and AI mathematicians collaborate, each bringing unique strengths. Human intuition, creativity, goal setting, combined with AI's unparalleled logical precision, tireless search, and massive computational power, pushing the boundaries of knowledge together in entirely new ways. It suggests a future of, perhaps, augmented mathematical discovery.
A truly thought-provoking idea to end on. We hope this deep dive has given you, our listeners, a comprehensive and engaging look at the technical details and the really profound implications of these advancements in AI and automated theorem proving.
Thank you for joining us on this journey into the depths of formal reasoning.